Okay, folks, this is going to be the first tablet-oriented problem. I don't know what's going to happen, so I'm going to do my best on this thing. We'll see where it goes. So this was these problems are straight out of the book. The solutions are in the book somewhere. And so let's go with this thing. So this is the first problem in the counter chapter, and it's some type of counter problem. And I know we're moving towards using state machines to control circuits and control things like counters, but this is not really a control problem. This is a straight counter problem. So if you look at this counter, it looks like it's counting 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and it starts back at 6. Okay, a normal counter would normal binary counter would generally count from 0 through 15, and it would overflow back to 0, etc., etc. So this is what you can see by looking at this counter. It's an up counter of some type. It's incrementing. It rolls over at 15, which is a maximum count for a 4-bit counter, and it starts again at 6. Okay, so what we want to do is take a standard counter and implement the circuit. So the very first thing you want to do in this circuit is get the drawing here. Get the drawing going is essentially write a black box diagram for this thing. So we'll do that right here. Get my hand off that button. This is top level black box diagram. It's a circuit. It has a count output, and it has a clock because it's a counter. And do I need anything else on this? I don't think so. What I need to do is fill in the width of the output count. Okay, if you look at this thing, the maximum value is 15. Everyone should know that as the maximum value for a 4-bit counter. So this is, in fact, a 4-bit up counter with a special load issue on this thing. Okay, so when we're going to do this problem, and the first thing we're going to note on this thing is probably at the heart of this thing is a counter. So I'm going to draw a counter as we know and love it. Okay. The output of this counter is going to be that 4-bit count signal. It's 4 bits. It has a clock input. I'm not going to write clock because it clutters the diagram up on this thing. So what I need to do here is take a normal counter with all the features of a counter and magically load a new value into this thing. Instead of starting at 0, I need to start it at 6. And the preferred way to do this is to load 6 when I hit the maximum count. So typically speaking, in a problem like this, I'm going to throw an RCO in there, and it's going to be used to load my new count here. This is connected to the load input. I have a data input on this thing, and I am going to hardwire that to 60110. There's my 4 bits for the 6. Okay, so really these are set up such that there's really no other way to do these type of problems. We always want to take advantage of that RCO whenever we can. Essentially, it tells me the max when it's hit its maximum count, which is what this is set up to do. So once again, I think what I'm going to do here, I'm going to call this done, and I don't know what else to say to it, but I know there's a timing diagram floating around with this thing. I'm going to go to that next. So let's do this. Okay, so this is the associated timing diagram. That you can see that the counter is counting up, 12, 13, 14, 15. When it hits 15, the RCO turns on. So what that is going to do is sometime right after that edge right there, that RCO is going to turn on. That RCO is connected to the load input, and so that essentially that load input is now going to be asserted. But since the load input is synchronous input, synchronous control input, it's not going to take effect until the next clock edge, this is the next clock edge. So it's this signal right here connected to the load that's going to cause the loading of the value of 6 there. And that, folks, is the first example on how this counter works. Not too exciting on this thing. Oh, of course, I forgot the back part of this thing. This is a 2-part problem. Okay, so this actually has more circuitry on it, and essentially it has an LED output that indicates when the counter is greater than 11. So this is somewhat of a trick. Yeah, I should have put the LED in here from the beginning, but that's okay. Design is circular, and I can go back and fix this as I need to. So anyway, this has an LED output also, and the issue is I need to figure out when it's greater than 11. So what I'm going to do here is take advantage of the fact that the weighting of a 4-bit binary number is 12448. This is the MSB. This is the LSB. And the issue here is if these 2 bits are set, then I know the count is greater than 11. Okay, 8 plus 4 is 12. So what I'm going to do here is just erase that. I think I have an eraser here. Whoa. That is high tech. Alright, so this thing, I'm going to put 2 signals on it. And I'm going to say this is CNT of 3. And this is CNT of 2. Those are the 2 most significant bits. If those are both set, the LED turns on because by all means that value is greater than 11. And once again, I think you can see that in the timing diagram. Once that value hits 12, that LED turns on, and there's the phone ringing. Anyway, folks, thanks a bunch.